All right, welcome back. We're going to finish this first lecture looking at tunneling through a square barrier potential. And the general idea here is, and we've done all the algebra before over and over, but what's different now is that the energy of the particles is less than the potential barrier height. Classically, they would all bounce off, there'd be zero transmission, but of course, quantum mechanically, I hate to break it to you, break the surprise, but particles, quantum mechanical particles, can make it through finite length barriers. So let's first think about what's going on in region 1 and 3 with the time-independent Schrodinger equation. We know minus h bar squared over 2m psi of x equals E psi of x. And we know that the solutions have the form of free particles, or just waves. We know psi 1 will have a component traveling right, that's your incident. Oops, leave that alone. Plus a back reflected traveling wave, which is possible and does happen. We also know in region 3 there's only going to be a wave traveling to the right. Only if waves were incident from right to left would we have a wave traveling left. And so C and D are reserved for region 2, so F is the coefficient for the wave function in region 3, and we have a wave traveling to the right. Both of these have your K1 as the 2me over h bar squared square root. Okay. Now region 2, of course, is a little different, right? And that's since the potential is greater than the energy of the particles. In region 2, our wave function, our time-independent Schrodinger equation looks like this. Oops, let me do it. Oh wow. Psi 2 and equal to E psi. We have done this before. So basically, subtract the V0 psi 2 from each side, multiply through by 2m over h bar squared with a negative. You end up with this. We have negative 2m e minus v0 over h bar squared times psi 2. All right, so we identify K2 as this, but the problem is, since E is less than V0, this number is going to be negative. So why don't we take a negative 1 out, have that cancel here. And we have 2m V0 minus E. over h bar squared times psi 2. Here we identify k2 as the square root of this mess. And because k2 is a positive quantity, and because there's no negative sign, right, we could just write it as like this. We know k2 is a positive quantity. Then this ends up being a different wave function altogether. So we have 2m v0 minus e over h bar squared square root. Cool. K2 is real, right? And so our solutions are exponentials. Therefore, psi sub 2 has the form of ce to the k2x plus d e to the minus k2x. And right, so these are increasing exponential, decreasing exponential with increasing x, of course. Okay, solving this is, as we saw before, quite similar to the prior work we've done with the square potential, the potential well and the potential barrier. So if we compare with the potential well, the analysis for t, really for the coefficients, analysis for t is identical to previous work. Everything is the same as long as, except we replace I k2 with just k2 everywhere we see it. So taking the solution for the transmission coefficient of the previous problem and just making those switches, we get 1 over 1 plus 1/4 v0 squared over e times e minus v0 but now the big difference is that instead of sine squared k2a, we have sine squared of I k2a. And that is something completely different. In fact, if you notice, it can be shown, ICBS, that the sign of imaginary number or a complex number turns out to be I times sine hyperbolic. Sinh or sin, sine hyperbolic. Well, that looked pretty ugly. Let's fix that. The sine of I k2a equals I times the sine hyperbolic of k2a. So then, transmission coefficient can be written like this. Right, let's see. It's the sine squared. Square this, same thing as squaring this. I squared is minus 1. And so we're going to get a negative sign here. Just don't want you to be surprised with this minus sign. And we have v0 squared for e times e minus v0. And now we have our hyperbolic sine squared. When was the last time you saw a hyperbolic sine squared? Cool. Grab a quick image of that. I'm going to blank it out. We want to look at one last little thing. So let's rewrite our transmission coefficient. 1 minus 1/4 v0 squared e times e minus v0 times our sine hyperbolic squared. Oops. Now what can we do with this? Well, we have to play around with it just a little bit. So first consider that sine hyperbolic. Well, I wouldn't expect you to know that sine of I phi is equal to I sine hyperbolic of phi. This shouldn't be such a stretch. Hyperbolic sine of an angle phi is equal to 1/2 the sum of exponentials, e to the phi minus e to the minus phi. Now, let's play around with that. I'm going to leave, right? We'll let phi equal k2a eventually. But now what do we do with sine squared? Hyperbolic. Oops, try it again. Sine hyperbolic squared of phi. Well, it's going to be this squared. So we've got a 1/4 times e to the phi minus e to the minus phi times itself, e to the phi minus e to the minus phi. Multiply that out. Get a 1/4. First term, e to the phi times e to the phi is e to the 2 phi. Let's see, the last term, negative e to the minus phi times negative e to the minus phi is plus e to the minus 2 phi. The outer term, e to the phi times e to the minus phi is 1 with a negative. The inner term, e to the minus phi times e to the phi is 1 with a negative, so it's a minus 2. Right? And so he says, for k2a, which equals phi, being much greater than 1, being very large, we can go ahead and start approximating that the sine hyperbolic squared of k2a, well, it's just going to be this term right here. If e to the 2k2a, which is what this is, if k2a is much greater than 1, this is going to dominate. This is going to be very small. And if k2a is much greater than 1, it's going to dominate this. So we approximate now. Sine squared hyperbolic of k2a is just this term with phi equal to k2a. E to the 2k2a over 4. So then our transmission coefficient. Looks like this. Basically replace this. I'll put an approximate here because we're now approximating. 1 minus 1/4 v0 squared and oops, what am I looking at here? E times E minus v0 like so. And then last, most important term, e to the 2k2a over 4. Now, if k2a is much greater than 1, this is huge, and it's much greater than 1. And so I'm going to ignore this 1. And so we're basically going to say it's approximately equal to 1 over, and I'm going to play a little sleight of hand. Take out a -1 by flipping the order of this. Cancel that -1. Oops, messed that up. E times v0 minus E. So basically maybe bring the negative in. Down here, negative E plus v0. Flip it around, you're good to go. E to the 2k2a over 4. So we'll combine the 4 together with the other 4 to get 16. And the transmission coefficient is approximately, bring everything up to the numerator, we're going to get 16 E times v0 minus E. That's 16. We have over v0 squared. I like that. Over v0 squared. And then now this is, you can write in the numerator as a decaying exponential. And this right here is the key. The tunneling probability has an inverse exponential and exponentially decreasing dependence. The tunneling probability which is really just the transmission coefficient. Tunneling means it transmits. So T is our tunneling probability most technically. Decays exponentially with K2A. Remember K2, so I'll remind you, K2 was equal to root 2m v0 minus e over h bar squared. The mass shouldn't change, the energy and potential shouldn't change because this is a time-independent problem. So really decreases with A. The larger the barrier, the wider your barrier, the more it decreases, the less probability, right? So a short, thin barrier has t greater than a wide barrier, which makes sense if we can believe that the particles actually travel through this. And they do. This is the whole concept of a scanning tunneling microscope. Not the whole concept, but the concept. You take a little sharp tip, you place it close to a conducting sample without touching it. You apply a potential difference between the tip and sample, and you get electrons that tunnel between that vacuum barrier. And Binig and Romer, I believe, Rohrer, R-O-H-R-E-R, received the Nobel Prize in Physics in 1986 for this. Even though it was around 1980-81 where they proved this to be true. It took a little bit, but they got their Nobel Prize. All right, that is all for the tunneling through a barrier. You can look further into Professor Woods' notes for more detail. The last thing we'll cover, not the last thing, the next thing we'll cover in this chapter is the finite depth potential well. Now that we know all about wave functions exponentially decreasing into a barrier. So I will see you later.